Yeah, our vision for the future of materials manufacturing is to think about developing a virtual or a digital factory that can run in parallel with an actual factory that produces parts. So we need to develop simulation tools to look at all the different processes that are involved. This really requires us to understand materials at a much deeper level than we do. And we think that starting with applications, we can drill down to the microstructure and all the way down to the atomic level, and then come back to the applications at the macro scale. My name is Warren Poole. I'm the head of the Department of Materials Engineering at University of British Columbia. I did my undergraduate degree at Western Ontario, and they have a general engineering program in first year. So we were introduced to all the different disciplines there. One of the professors from materials engineering came by, and he showed us a demonstration of the Sharpie impact energy of steels. And they tested steels that had been quenched, and they actually did the quenching right on the stage during the demonstration. So you could see when the steel was started, it was very ductile and it absorbed a lot of energy. But after they quenched it, the steel was completely brittle. And I was just fascinated by how a material, iron, could change its properties so much just by what we now know as the sort of the thermal history and things. But at that time, I didn't have any idea, but it just seemed fascinating to me. So Magnet was what's called an NSERC strategic research network. So the idea here was to build in Canada a group of universities to study a problem of strategic interest to Canada. So we brought together 5 universities and a number of industry partners, 2 government laboratories to study the development of magnesium materials for the automotive sector primarily. So when you want to do a big, new, exciting program, you can't be looking at incremental changes. So magnesium is very interesting because it can make a transformational change in the weight of a vehicle. So magnesium, for example, has 20% the density of steel. It's 80% lighter. So this really has the opportunity to be a game changer in the automobile industry. So we looked at it from 2 points of view. The fundamentals, so developing things like thermodynamic databases, basic information on how magnesium deforms. Then we looked at thermomechanical processing, followed by heat treatments. We went on to study the formability of the material, and finally to think about how we could join the magnesium components with other components made out of steel or aluminum. So we tried to go through that entire process chain with the goal to produce a component. The challenge of running a project like this is to coordinate all the activities between all the different universities, the government labs, the industry partners. We were actually, I think, quite successful there. Again, working with our industry partners closely. General Motors, Magnesium Electron provided us with some sheet. Magna provided access to their stamping plant. We were able to take the ZEK 100 sheet that had been processed by Magnesium Electron and form it into a complex magnesium door inner using a warm forming technology. So this was really a breakthrough because we were able to form such a complicated part at relatively low temperatures with unheated dyes using conventional lubricants. And the parts could be formed very fast, less than 10 seconds to make each door inner. So this represented a real step change over other processes. We really think we made a step towards a viable production route that could be used on a large scale. I think this is very much the future model that we'll see more and more of, is that excellent researchers in Canada teaming together to tackle complex grand challenges that we face. And I think this is true across all fields, not just the materials engineering field.